that appear in the eigenvalue problem are invariant and coordinate transformations. I just want to point out this is valid for any general matrix I have given, but actually the proof is quite simple. For an arbitrary n by n matrix, you don't even need the additional requirement of an orthogonal transformation. It is valid for general transformation, invertible transformation. So, to understand that, suppose let's say I have A, which is an n by n matrix, let's say it's a squared matrix, for which the eigenvalue problem is defined. Right? So, if we now look at the eigenvalue problem for this, it will be so what is an eigenvalue? Eigenvalue is, suppose I have a vector x which is not equal to 0, for which this equation is satisfied, then we say that lambda is an eigenvalue of the matrix A. Right? But an eigenvector, maybe I will use x, I will just psi. With an eigenvector that is given by psi. So psi is the corresponding eigenvector. Now it's possible to prove that suppose I consider a matrix P, only requirement is that it be inverted. Of course, that's also n by n. Right? Then it is possible to show that the matrix P inverse AP has the same, we can say, spectrum, that means the same set of eigenvalues as that of A. Whatever, if lambda is an eigenvalue of A, it is possible to prove that it will also be an eigenvalue of P inverse AP. But that's not all there is to it. If some lambda is an eigenvalue of P inverse AP, then it is also an eigenvalue of A. What this means is there is a one-to-one correspondence between the eigenvalues of A and that of P inverse AP. So what is P inverse AP represent? Right? Looking at it as simply multiplication of three matrices, right? But it has a significance beyond that. Right? The significance is, just as I pointed out, if I have a vector which has a certain, let's say now it will be x1, x2, xn. Let's say I represent a vector. Right? So the vector is identified principally by means of the components of the vector in a particular basis set with respect to a particular basis set. So when I say x has components this, I am also simultaneously referring to a basis set E1, En. Now if I consider another basis set E1 bar, En bar, then the same vector which has components x1, x2, xn with respect to E1 will have the components, let's say x1 bar, xn bar. What is the relation between x1, x2 and xn on one hand and x1 bar, x2 bar and xn bar on another hand? Right? That is what we define by the matrix L in the one of the earlier cases, but I can now use because L I want to use for an orthogonal transformation. If this is not an orthonormal basis set, and we are considering, transformations between bases which are not orthonormal, then the matrix P need not necessarily also be orthogonal. Right? So if I now consider the relation would have the following form. I can relate the components of the two by this. You can write it like this. Now what is P? P is simply the transformation matrix that defines the transformation between E1, E2 and En on the other one hand and E1 bar, E2 bar and En bar on the other. So the basis sets are not orthonormal. I have to bring in what are also known as the reciprocal basis set corresponding to this and corresponding to this to define the matrix P. P is some matrix that defines this transformation. It would have dot products of the unit vectors in the two, or the basis vectors in the two sets. Now, that P is what is also appearing here. Now, when I am talking about an n by n matrix, now n by n matrix, right, converts a vector in the Rn space into another vector also in the Rn space. That means we have n elements. Okay. So when I am given a matrix, I can operate it on a particular vector and it will transform into some other vector. In this case, because it is n by n, the net result will also be another vector in the same space. But if I have an m by n, then that will convert an n vector into an m vector. That is acting between two different spaces, but this is between the same space. But now when you are given a matrix, right, you have to understand, you can ask, what is the relation between x and x bar, which is given by this, very similar to if I now call this, let's say, a bar, the relation between a and a bar. So we can also have to regard here both a and a bar as two representations of a single linear operator or a linear transformation. So both a and a bar are simply matrix representations of the same linear transformation with respect to two different basis sets for V. Right? So what that means is that now A would be, is acting on V to V. So, but I have a choice of basis sets for V. If I choose E1, En, let us say that matrix representation is what is given by A, right? Then, if I choose E1 bar, En bar, then it is possible to show the matrix representation of the same operator, which has a representation A. So I can call the operator as A hat. Right? This is a vector. Right? Now the vector, what is the vector here? Vector has a representation x1, x2, xn with respect to this basis. Right? It has x1 bar, xn bar with respect to this basis. So what is the vector itself? Right? The vector itself we don't directly access. We only say we are referring to one vector which has a certain set of components in one basis set and it has a certain set of components in another basis set, and this is the relation that gives the way the components of the vector itself would transform. Right? In the same way, I would regard A matrix and A bar as simply two representations of a single linear transformation. Only thing is that the basis set used for the vector space, the two cases are different. And just as this gives the relationship between the representations of the same vector in the two different basis sets, I can regard this as giving the representation of a linear operator, right, when I am choosing the two different basis sets. That's how you have to look at it. This is never, because when I am given a matrix, right, when you are given a matrix and you are asked to find its eigenvalues, you have to first understand that that matrix in a more deeper level is a representation of a linear operator with respect to a particular basis set. You are never given what that basis set is, right? But then suppose I give you, for the same linear transformation, I give you the matrix, let's say A bar, which has a different representation because I am now referring to a different basis set, then this is the relation between the two basis sets. Now if I give you that matrix and ask you to solve the eigenvalue problem, will the eigenvalues you obtain be the same in the two cases? Right? It will be the same, and that is what, if you are able to prove this, that is what it says. So it doesn't matter which representation in which you are given an operator, if you solve the eigenvalue problem, it will be the same. The eigenvectors will be different, obviously. Eigenvectors of P inverse AP and A are not the same, right? The eigenvalues are the same, right? So this is one way of proving it. Another way is, suppose I have given the matrix A. One way I will solve for the eigenvalues is the determinant of this is equal to C. I am not actually going to prove any of these, but you can easily prove. Now you can also prove, so this establishes that the eigenvalues are the same. Now if the eigenvalues are the same, then the characteristic equation has to be the same. So every coefficient in the characteristic equation has to be the same. I can infer that, right? Because two sets of characteristic equations are giving the same eigenvalue. All the eigenvalues are the same. Then the two equations are obviously the same. So every term in that equation must be the same. So this is one way of proving that the coefficients in the characteristic equation are invariant under coordinate transformation, not coordinate, under a general transformation given by this P inverse of P, right? Because I have not here made use of the fact that P transpose equal to P inverse. That is what we normally refer to as a coordinate transformation or a orthogonal transformation. So that is one way of proving. Another way is, if I am given a matrix A, right, this is how I would solve. If I am given P inverse AP, I would solve clearly equal to 0. So it is possible again to prove that the determinant of A minus lambda I is the same as the determinant of P inverse AP minus lambda I. Right? So again I have proved, that's another way of proving that the characteristic equation by A minus lambda I and P inverse AP minus lambda I are the same, because the determinants of those are the same. So A and P inverse AP have the same eigenvalues, and hence each and every coefficient in the characteristic equation must be the same. So that is also invariant under transformation. But what another probably more roundabout, very direct way is to take each and every coefficient in the characteristic equation, right? It is very difficult to give a general formula for an nth order matrix. You can start with lambda power n. So if I make this positive, right, then the next one would have maybe minus trace 8 lambda power n minus 1. Right? We can also give a formula for, that is what is given here, the phi. So this is the theta that I have. You can also give balance. This would be half times ai squared. This is nothing but the base of a. So I can want to the base of a squared minus aij. Here I am introducing the repeated index summation. So aij is also the trace of a certain matrix. So can you tell me what that matrix is? It's also the trace of a certain matrix. A squared, right? That can be easily shown. So I can write this generally as minus trace of a squared. The two are different. The base of a, take it squared. This is take a squared and take the trace of that. But it's very difficult to write the other formula for all the other coefficients. Yeah, this will be lambda power n minus 2. I'm not going to write any of the others. It's difficult to give a general formula. I have to introduce the notation for, the permutation symbol for arbitrary number of variables. So I'm not going to do that. But the final one constant will always be minus determinant of A. So another way to prove the invariance is go term by term and prove it. That is what you have been asked to prove, but actually it is not required. First of all, we don't even require the fact that P inverse has to be equal to P transpose. This is valid for the general transformation. But here you are asked to use a special form for a 3 by 3 matrix alone. And you are asked to go and prove that each and every coefficient is invariant under only coordinate transformation. That means you can assume that the L that we are considering as the matrix of transformation of coordinates is actually L transpose equal to L inverse. That's an orthogonal transformation, but I can actually prove it without invoking that. I will demonstrate that. So when you have n equal to 3, this is squared, the coefficient of lambda squared. This is the coefficient of lambda by n is equal to 1, and this is the constant. That's all we have for the 3 by 3 matrix. That's exactly what we have here. Now we take the trace. Let's take the trace. Trace is represented by AII. Now I am using the repeated index summation convention. Right? Trace. Now trace is invariant under transformation. So trace actually is the sum of all the diagonal elements of A. Right? So now I am considering a transformation. I will not consider. I will prove it without invoking the fact that actually the L matrix that we have considered earlier, that the transpose is equal to inverse, we won't consider that. So now L inverse. So I have AII. Now the trace in the transform case would be AII bar. So what is the relation between AII bar and AII? I can easily establish that by looking at the relation between A bar. What I mean by invariance is this: when I transform the coordinate system, all I am going to get is L inverse A L. The A bar, every element of A bar is given by this, right? So all I need to know is the product rule for multiplication of matrices. Suppose I have this matrix B and C. Let's, for the simplicity, assume that this formula is valid even for non-square matrices, provided there is a match between the columns of B and the rows of C. For simplicity, we can consider square matrices B and C n by n. So there is no problem with respect to whether you want to post multiply or pre multiply. So if we have BC, what can we say about BC, the ijth element of BC? How can you write it? Ijth element of BC in terms of the elements of B and C. Bik, Ck. Normally we put k into 1 to n, right? But here I won't use it because I am using the repeated index summation convention. So under the repeated index summation convention, an arbitrary element of the product of two matrices B and C is given by this. Now I can extend it to any set of matrices. Suppose I want the product of 3 matrices, then I can write this as Bik. I don't need another index, right? Ckl Dlj. Right? That is what would be the ijth element of a product of 3 matrices. Right? So the ijth element, if I write of A bar, it would be L inverse, right? Ik, I can just directly follow that, right? A Kl L Lj. If I make j equal to I, if I make j is equal to I in this, then I make j equal to I in this, right? the ith element, a diagonal element corresponding to, let's say, I equal to 1 or 2 or 3, provided I don't sum over I. But if I leave it as it is, under the repeated index summation convention, what does this represent? The trace of the matrix A bar, right? So, because I wrote first, this is what you have to understand, that the repeated index summation convention can be confusing. Because I first wrote Aij, that refers to a particular element, any element, maybe diagonal or off diagonal. So this formula is valid not just for 3 by 3 but for any n by n matrix also, right? So I don't even have to restrict myself to a 3 by 3 as it is given in the form. Right? So this is what it is. So if I want the diagonal element, since this is a formula for any element, if I want the diagonal element, then I make it I. But I have to remember, since I have used the repeated summation convention for K and L, if I want the ith element, I have to caution and say that no summation over I. I have to say that. But however, now what I want is a trace directly, not just the one diagonal element. So now if I remove this, then that means it's summed over I also, that means summed over all the diagonal elements. That will give me the trace of the product of the 3 matrices, which is A bar. Right? Now can you prove that this is equal to the trace of A? How would you prove it? You have to sort of rearrange the product of 3 terms. I have to rearrange. How do I rearrange so that I prove what I want? What would you do? Comment it. If you think of a way. Transpose I am not going to use. If you want, you can use it. But I want to prove it without using the fact that L inverse is equal to L transpose. Can you prove it? What if I write this as, this is just a product of factors, I can simply write it like this. Now can you tell me what you see? Do you see now any improvement? What does this represent? L inverse Ik represents what? Represents what? That's what I want. I do what I L inverse Ik represents which element? Lk element of the product of the 2 matrices L and L inverse. You jumping to the answer, right? Clearly, that's what it represents, right? And then I have AKL. So L inverse, I know that because one condition on L is that it should have an inverse, but it is equal. The L inverse is equal to L transpose or not. You can see that I am not going to use it to prove this. So L inverse. Lk, what can you say about this? It is the L inverse with the identity matrix, right? The L inverse, the Lk element, what can you write? Delta Lk, the chronic delta AKL. So this is K equal to L. This would be ALL, which is clearly the trace of A. Right? So this is the trace of A bar, which is equal to trace of A. So I have proved that the trace of A is equal to the trace of A bar. That means the trace is invariant and the transpose. Nowhere have we used the fact that L transpose is actually to an L inverse. So that's what you expect even for an N. Nor have we used the fact that it is a 3 by 3 matrix. It's valid for any n by n matrix. Right? The same way, if you go look at the determinant, right? If you look at the determinant of A bar. So A bar is, I can do it different ways. You know the formula of the determinant in terms of the epsilon I T A. You can do it that way. But an easier way is to simply make use of the well-known result in matrix algebra that the determinant of a product of several matrices is simply the product of the determinant. So if you take that result, so I clearly get that the determinant of A bar is the determinant of L inverse times the determinant of A times the determinant of L. So I can now combine these two. This is the product of determinants. So I can write this as determinant of either L inverse L or L inverse times determinant of A. So this may be the unit matrix of determinant is equal to 1. So I proved that's a very easy way of proving it. If you want to go through the indices, then you have 3 indices A1I, A2J, A3A. You have to transform it. That's going to be quite a job to do. But you can get a clue. Suppose now I want to solve a second invariant. How do I prove that? Second invariant is given by the symbol phi half, right? AI squared minus AIJ AJI. I write it in this way. I can also write it in place of A squared, right? But so this part, I know that is invariant. Because place of A I have already proved is invariant and the transformation. So the corresponding, so if this is phi A, then phi A bar, the A bar is given by that is R AI bar squared minus A bar IJ AJI bar. I have already proved that AII is equal to AII bar. So the trace of A bar are the same. So all I have to do is to prove that AIJ AJI is equal to AIJ bar AJI bar. So how could you prove this? So let's take, I have the general expression here, AIJ bar. I have the general what I did here. L inverse Ij. I have already the general formula, right? So now, so I want Aij, AJI bar. So what would you write for AJI bar? AJI bar, when you write the general Jith element, I have written the ijth element, I want you to add it or multiply it here. So this is, now I want you to write AJI bar on that side, written after the brackets. Obviously, you are going to change I and J, but there is a catch because we are using the repeated index summation convention. You cannot use the same K and L, you cannot use. L and K cannot be interchanged, right? I and J will be interchanged in that. Yeah, first you write at least that. But summation indices, because it's not coming in the product, I have already used K and L as summation index. So you have to use something else. Right? Because AJI bar is again a product of 3 matrices. Yes, L inverse, what would be the first term? Please write that. JI, I want the JI element. So I would have to replace I with J. Good. Now K and L I am saying you cannot use anymore. because they've already been used. So you put M, good, very good. And then A, M, L again you cannot use, you can use N or whatever, right? And A, N, and sorry, L, L, L inverse A, L, L, N, I, M, N, L, N, I, yes. Fine. Now, which one you would bring together? The answer is there. The same trick that I used for the trace, we have to use here. So, how would you rearrange the L and the L inverse terms to make some of them unit or delta? The chronicle delta would come in. So, which one could you join? Yeah, I would write that before that. Right, so there is a sum over I. Anyway, let's see what you get. JM. Yeah. And then AKL. AMN. Yes, now which one would you combine? Right, probably the elements of the product of the matrices. What is the L inverse IK, L N I? What element of what matrix does it represent? That's what I want you to figure out by using the product rule. NK. Yeah, so IK. So it's an nth element of L inverse, so you can replace it by delta nk or delta kn, it doesn't matter. Right? Yeah. Fine. Yeah, then this one L inverse LMJ, LJM, so that will be delta LM. Fine, so I'm going to write that. Delta NK, delta LM, AKL, AMN, right? So I have to make K equal to N, right? No, don't do that. Whichever way, you can replace K by N throughout or N by K throughout, it doesn't matter. N equal to K and L equal to M. So you have only 2 indices instead of 4 indices. So, how would you write it? You write the final form. A, K, M, A, M, K. AKM, AMK. Is this the same as AIJ, AJI? It is the same. Only thing is that because here it is not referring to a particular, yeah, that's fine. You can now go back. Referring not to a particular element, it's the sum over both I and J. So there's nothing special about IJ and J here, as all I have replace is the summation index K. If I replace it by I, the summation index M, if I replace it by J, right, I get the same thing. It's the same because it is just a dummy index of indices of summation. So there's nothing special about I and J or K and M or whatever it is. If you had, for instance, replaced K by N and M by L, that would still have been fine. It would have been the same. It's a scalar, it is sum, right? So there's no element of any particular vector or matrix that comes in, right? It's just a sum of different elements of A. That's all. So we have also proved that the second invariant, the second coefficient, the characteristic equation of a third order 3 by 3 matrix is, which is what we now call as a second order tensor. Representation is the form of a 3 by 3 matrix, right? So you can see that nowhere I have made use of the fact that actually L inverse is equal to the L transpose, which is what you expect based on what I didn't prove, but these are also very easy to prove. You have the general result, then there is no need to prove any of it, but it is still useful because it helps you to understand the way the indices work. That is the only reason. Otherwise, the result is there in matrix algebra. So that n by n matrix, and in fact, not even an orthogonal transformation, but even general transformation. Orthogonal transformation you get, right, when you transform from an orthonormal basis set to another orthonormal basis set, which is what we are going to consider in the predominantly in this course. Right? Yes.
Sir, is this valid for if the eigenvalues are repeated? Is this transformation valid if the eigenvalues are repeated?
Yeah. It doesn't say anything about the point we will come, whether it doesn't say only about the characteristic equation. It does not say what the eigenvalues are going to be. Right? It doesn't say anything about the nature of the eigenvalues, only it says about the characteristic equation. We have not gone into whether the eigenvalues are even going to be real or complex or repeated or what the geometric multiplicity, algebraic multiplicity and all this. Purely the characteristic equation. All this says is the characteristic equation does not change under coordinate transformation. That's all. The coordinate transformation can also be between non-orthonormal basis sets. There it is more difficult to arrive at the formula for P and P inverse, but here, even restricting ourselves to coordinate transformations which we mean by orthogonal transformations, what I was going to say was the two basis sets E1, E2, En and E1 bar, E2 bar, En bar, they need not be orthonormal. They have to be a basis set, which means every vector has a unique representation in terms of those vectors in the basis set. That is the criterion for the basis set. The basis set need not be orthogonal or orthonormal. Right? But if you make a transformation from one basis set to another, then the matrix P also will not be an orthogonal matrix P, in that P inverse will not be equal to P transpose. However, if you are going from an orthonormal basis set to another orthonormal basis set, which is what we are doing here. What I am saying is that what we are considering effectively is a rotation of the axis. It's a linear transformation. Right? Rotation of the axis, I have drawn it in terms of 2 dimensions. Right? So I am going from one orthogonal to another orthogonal. That's a simpler, more special case, in which case you can prove the transformation matrix P could actually be orthogonal, in which the P transpose would be equal to P inverse. But for proving the invariance, I don't have to use that. However, for the rest of the proof of the Stokes relation, that is used. The fact that it is a coordinate transformation is used. So if you look at the proof closely of the Stokes relation, right, then that will come into place. So let's now recollect, right, the context in which this problem arose. Right? Context in which this problem arose was the Stokes hypothesis. It says that now we will come to the problem that you raised, whether the eigenvalues have to be distinct, real, repeated, whatever. That will become very important when we try to give a proof of the final result. So this is the one. When we said here we are restricting ourselves only to coordinate transformation. So in this case, I am going to replace L inverse by L transpose to make it clear. So the second hypothesis is that L transpose strictly should be L inverse only. L inverse is the basic quantity that comes in the transformation. And since we are considering only transformations which go from one orthonormal set to another in the rectangular coordinate system, I can replace L inverse by L transpose is equal to F of the second hypothesis. The problem is most important, and then D equal to minus I plus equal to when D is equal to C. Then we said, so we can call any fluid that satisfies these hypotheses as a Stokesian fluid. this is by no means a unique set of hypotheses. Different types of fluids, might be fluids which do not fit into the idea of a Stokesian fluid. We may regard as any fluid, certainly the Navier-Stokes fluid or the Newtonian fluid would fall into this category. Right? There may be other fluids for which this hypothesis might not be sufficient, or might have even to remove one of them, right? And so that would form a different class of fluids. So these are not as fundamental as the continuity equation and the equation of motion. These deal with separate special classes of fluids. One broad class of fluids is the Stokesian fluid, which includes as a special case the linearly viscous fluid or the Newtonian fluid. Right? Under these hypotheses, it is possible to prove, which I haven't yet proved, nor are we really going to prove it in the most general manner, that the stress tensor necessarily has to have this form. Right? So this is a tensor relation. There are 9 elements on the left hand side and there are 9 elements in each of the terms in the right hand side. Of course, this is just alpha, beta and gamma, as I said, are scalars, but they are functions of the invariants. That is when we introduce the notion of invariance. So that is very important. Alpha, beta, gamma are scalar functions of the invariance of D. The invariants are also invariant under transformation. That's why they have been included. They need not necessarily be constant. So you can prove that this is the most general form of the relation between stress and the deformation tensor under these hypotheses. What's important is to understand the significance of the result. Now, to give a proof of this, I'll give an outline of a proof and complete it in the next class because we're running out of time. As I said, where the idea of the eigenvalue problem will come in, once we have already introduced the invariants and they are the coefficients that appear in the characteristic equation, we will see that it simplifies the proof considerably if we move to a coordinate system where P and D are diagonal. That is where the representation comes. So I have talked here about P inverse AP. Now I can ask, for a given matrix A, does there exist a basis set for which P inverse AB is diagonal? Right? That means P inverse AB, if you consider any number of coordinate system, P inverse AB will be some other matrix which has in general all 9 elements. But we can pose the question, and this is related to the eigenvalue problem. This is what leads to the eigenvalue problem actually. We can pose the question whether, because it may not always exist, whether a particular transformation of coordinates or basis set exists where P inverse AB is fully diagonal, and that means that it has only the diagonal element. There is no problem that can be posed for a general square matrix, not just a 3 by 3 matrix. We are interested only in 3 by 3 matrix. We have to always keep in mind the more general form. Right? How is that related to the proof of this? We'll see in the next class.